So again, we may see some other inverse Laplace transform problems where the form of it doesn't match any of the examples in our table of Laplace transforms. And in many cases, we can use partial fraction decomposition to write something that doesn't look familiar to us into a form where we can use what we've learned from our tables. So if we see something like this, notice this would not be in our tables for Laplace transforms. But we notice we have a fraction where we have two linear factors in the denominator. And we learned back in calculus, if you have a situation like that, you can rewrite the fraction as a constant over the first factor plus a constant over the second factor. So that's how you handle linear factors with partial fractions. Now here's the trick. We just multiply both sides of this equation by the denominator. That's all we're doing here. So when you do that, you get 1 on the left-hand side. Here, the s's would cancel, so a gets multiplied by s plus 1. Here, the s plus 1's cancel, so b gets multiplied by s. Now, when you were in calculus, you might have learned something called the cover-up method, and what I'm doing here is the equivalent to that. So when you do this, you have the linear factors. You can pick out certain values of s that cancel those terms. So for example, if you put s equal to 0 into this expression, right here you'll get a 0. So if we substitute s equal to 0 into the equation, we get 1 equals a times 0 plus 1 plus b times 0. From all of this, you just get a. So a is 1. Now, if you replace s with negative 1, you would cancel that term. So when you substitute negative 1, you get 1 equals a times negative 1 plus 0, which is 0, plus b times negative 1. You get a negative b there, equal to 1, so b is negative 1. So that tells us our constants in the partial fraction decomposition. So this number is a, and that one is negative. This one is 1, and that one's negative 1. So this is what we have here. 1 over s, a was 1, minus 1 over s plus 1 because b is negative 1. So that's what this is equivalent to. Now, why did we do it? Well, we know how to take the inverse Laplace transform of each one of these terms. So the inverse Laplace transform of the problem we started with is just the equivalent to the inverse Laplace transform of this expression. We know inverse Laplace transforms are linear, so we take the inverse Laplace transform of the first term minus the inverse Laplace transform of the second term. Inverse Laplace transform of 1 over s is just 1. This is just like 1 over s minus a, so a would be negative 1. That's e to the at, that would be e to the minus t. Now here's one. Again, if we were given this problem, this is not something that shows up in our table of Laplace transforms. In the denominator, we have a linear factor and a quadratic factor. So we handle the linear factor just like we did before. For a quadratic factor, we need to put bs plus c in the numerator over that factor. Again, we just multiply through the whole expression by that denominator. So what happens? The denominators cancel. You're left with 2s squared plus 1 on the left. S cancels. You're left with a times s squared plus 1. The s squared plus 1 terms cancel. So you're left with the factor bs plus c times s. Now this time, instead of plugging in numbers, let's expand it and compare like terms. So we just multiply a times s squared plus a times 1. bs times s gives you b times s squared. C times s gives you cs. Now, we have an s squared term and another s squared term. Combine those. The coefficient will be a plus b s squared. You have a c times s term, and you have a constant a. So when you compare the like terms, notice there is no s term on the left, so this c right there has to be 0. The coefficient of s squared on the right is a plus b. Coefficient of s squared on the left is 2, so a plus b is 2. And then the constant term is 1 on the left, and it's a on the right. that tells you a is 1. So you know a is 1, you know a plus b is 2, so 1 plus b is 2. That tells you b is 1. So we know all of the numbers a, b, and c. A is 1, b is 1, and c is 0. So that's what goes in up here. A is 1, b is 1, and c is 0. So that becomes, that's what we have here. So we have 1 over s over s squared plus 1. We recognize these from our tables in our previous work. Inverse Laplace transform of 1 over s is 1. Inverse Laplace transform of s over s squared plus 1 is cosine t. So that's pretty easy at the end. So we started out with one we didn't recognize, did partial fractions, and then got some really simple inverse Laplace transform problems at the end. Now, in order for the inverse Laplace transform to exist, we need that the limit as s approaches infinity of f of s to be 0. So for example, if I ask you what's the inverse Laplace transform of s to the 5th power over s squared plus 1, you would tell me it does not exist. Why? Because the power in the numerator is the 5th power, the power in the denominator is 2, that power is larger, so this limit's going to go to infinity, which is not 0. It has to be 0. So if you think back to all the formulas in our tables, all of those expressions, the limit as s approaches infinity of those expressions are 0, like a 1 over s minus a 1 over s squared plus k squared, things like that. All those have limits of 0. Now this one looks weird. Now we have the inverse Laplace transform of s to the 4th minus s squared plus 1, all divided by s to the 6th. Now notice the highest power in the numerator is the 4th power, highest power in the denominator is the 6th power. So what do you think there? The numerator has a lower power than the denominator, so that will go to 0. You might remember L'Hopital's rule. You could apply that there, but it's just, you can look at the powers. This would kind of behave like s to the 4th over s to the 6th, or 1 over s squared. Now, what do we know about this? This is just has a complicated numerator over a really simple denominator. You can just write it as 3 different fractions. S to the 4th over s to the 6th minus s squared over s to the 6th plus 1 over s to the 6th. Now all of these are like problems you saw in the table of Laplace transforms. You have to change the format just a little bit. That one's easy. That one's just t. This one, if you have a 4th power in the denominator, you need a 3 factorial in the numerator. You make it 3 factorial, you have to divide by 3 factorial. You need a 5 factorial here, so you have to divide by 5 factorial. So now we have t, 1 over 3 factorial, that one's t cubed. 1 over 5 factorial, this one's t to the 5th. If you expanded those, 3 factorial 6 and 5 factorials 120. So that would be the inverse Laplace transform. So don't let a problem like that bother you, because you can just divide each term by the denominator.